Hello and welcome to our next segment of Graphing Rational Equations, titled helpfully Holes. No, I'm not going to ask you to go out and dig any holes. I'm talking about holes in an otherwise continuous graph. So, the big questions: where do they come from? Can we get rid of them? Just answered the what are they anyway, a hole in an otherwise continuous graph. So let's go and start by looking at a problem that we've looked at before. Problem 1 from the last word. Remember problem 1? We had a fairly easy problem here with a vertical asymptote where we'd have division by 0 at x equals 2. And we have a horizontal asymptote on the x-axis because the highest power of the denominator is greater than the highest power of the numerator. There's no x-intercept because 3 is never going to be equal to 0. And we did a whole bunch of work that found our curves to be right along here and right along here. So if I multiply this part of the equation by 1, I should get back the same thing, the same equation with the same graph, right? I'm just multiplying it through by 1. We remember that we have the same line if we can divide the whole line by something and get the same number. So if I multiply one side of an equation by 1, then I should still have the same equation. It is, after all, the identity for multiplication. But I submit that it's not going to be quite that simple. So let's look at a clean copy of problem 1 and see what happens when we multiply it by 1 in a special form. All right, let's try out this multiplication by 1. And I told you I wanted to multiply by a special form of 1. In fact, I want to multiply by x minus 5 divided by x minus 5. Well, we said, or I said, that we had a vertical asymptote wherever we had division by 0. But if I do this multiplication, I have another place where I could have division by 0. But I already know that this should be the same graph that we just looked at. So I wasn't telling you the whole truth when I told you that we would have a vertical asymptote everywhere we would have division by 0. If I have what I call a removable discontinuity, or a hole in the graph, then I'm not going to have a vertical asymptote. But I do have a disallowed value for x. X cannot equal 5. We'll talk about how we can fill the hole in just a moment. If I said that x can't equal to 5, but this is really otherwise the same graph with our same horizontal and vertical asymptotes, well, in the work I did before, I found out that if we looked at the problem before we multiplied by x minus 5 over x minus 5, then the value at x equals 5 was 1. So that's where our little hole is going to appear in the graph. And if we look at that hole, then we're just going to otherwise have the same curve that we had before, just now with a hole in it, approaching my asymptotes. And I'm going to have this same curve going on over here on the other side, approaching my asymptotes infinitely in this nice little curve. So this is how a hole is formed. I have a factor in the numerator that is the same as a factor in the denominator. So x minus 5 here and x minus 5 here, and most of the time that you're going to see this in expression, it's not because you're going to have watched me multiply it in, it's because you're going to factor the expression and discover that there is a common factor, a common expression in the numerator and in the denominator. And those are what we call removable discontinuities, or holes, and they are not going to give us vertical asymptotes. That's why it's important to factor the numerator as well as the denominator. So how do I fill this hole? Well, I just create a piecewise function. I say that f of x equals this when x is not equal to 5, and f of x is equal to 1 when x is equal to 5. So I've just defined this as a piecewise function and filled in my hole. In the next video, we're going to put this idea of holes together with all of the other pieces of graphing our rational equations and graph equations from start to finish for the remaining 3 problems on this video worksheet.